Hello all. Welcome to the next lecture. We are going to talk about refraction of light at plane surfaces. This is your chapter 4. Now, generally in class, we talk and means there are jokes going somewhere, someone is disturbing and so on. But here when I teach means it becomes too like I have to concentrate only on the topic and so on. I can't crack joke like this. So I thought I will start this chapter with a poem on light. So as I explain my poem, I will explain you the meaning also, because see, in English literature, poem can have any meaning, right? Depends. But in physics, it should be clear, right? So it is a poem on light. Let's start and don't fight. Okay. So it goes like this. Light doesn't have any voice. Reflection, diffraction, interference, polarization are its choice. So light doesn't have any voice. Reflection, refraction, diffraction, and whatever I said are its choice. Means whenever light goes, there are some phenomena which takes place, like reflection, refraction and diffraction and polarization and so on. Okay, now next line goes like this. Light undergoes deviation. Okay, so light undergoes deviation and produces shift. I will talk about it. So you know that okay, you know from your earlier experience that from prism light can deviate and so on. So for that, light undergoes deviation and produces shift, which is a gift. So what happens due to this deviation? Actually, there are too many phenomena which is called dispersion and so on. So it is a gift. Light is a part of electromagnetic wave spectrum. So actually light is a part of electromagnetic wave spectrum. It is extended from X-rays to radio waves. Light is one part of it. So whatever we talk about light, it is true for entire spectrum, X-ray or UV ray and so on. So I will repeat it again. Light is a part of electromagnetic spectrum and possesses a lots of tantrums. Tantrums in the sense, the poet wants to convey that tantrums in the sense it has so many beautiful displaying of nature. So we see rainbows, we see dewdrop, we find it very beautiful. Then there are so many things in nature. Okay, rainbow, then aurora borealis, centralis, so many tantrums light have. Now next line goes like this. In light, electric and magnetic field varies with time. So if you can recall any wave, a wave is a disturbance, right? So at a point something changes. So suppose you have water wave, so height of the water will change. In case of light, it's more like abstract actually. In case of light, at a point, electric field and magnetic field changes. Okay, you guys will understand that thing later, but at a point something changes. So in light, electric field, magnetic field varies with time, which sounds beautiful like a chime. Chime, I guess you guys know. I myself don't have in my house, so they are arrangement of something. When wind blows, they hit each other and they produce a beautiful sound. I guess you know that. So in light, electric and magnetic field varies with time, which sounds beautiful like chime. Which is amazing actually. Even you can't see, but there is something changing. Last line. Without light, we can't think. Of course, if there is no light, I guess you all can think that there will be no civilization. So without light, we can't think, and our race will sink. Right? Okay, that is the poem. This is about light. I hope I have not bored you. If you like the poem, then let me know. I also want to become a celebrity and so on. Now we'll start the topic. This is chapter 4, refraction of light at plane surfaces. Okay, now in front of me means I can show you this experiment, and I will urge everyone to do it so that at least you know what you are doing. So I have a pencil here, glass, and as you dip that, uh, outside medium is air and this is water. Plenty of weird things actually happens. Okay, there are plenty of observation you can do one by one. You can look it from this side and see that it looks magnified. If you look from the top, it looks bent, and so on. Okay, yeah, you can watch it from different angle. So I want you guys to do this. This is one of the best example of refraction. So if you look at the, if you look from this angle, right, actually correctly, if I look at this angle, I can see the pencil bent like this. Okay, we'll talk about it. So this bending phenomena, as we define refraction, in refraction light rays going from one medium to another medium bend. Now we'll talk about it. So here the light, if you can see, is traveling from water to air, right? So you can imagine this pencil to be source and this is the medium. So light is coming out. It is coming out in such a way that I can see the pencil appearing to be bent. Okay, like this. I will urge you guys to do this experiment and observe it. Okay, there are plenty of things, okay, which can be explained here. Now moving on, in case of this refraction, from your earlier classes, I guess you can recall, refraction is when light bends while going from one medium to another medium. Now what happens is this, that as the light bends, and now light is a wave, so it has three things with it: frequency, wavelength and speed. I will write this is frequency, this is wavelength, and this is speed. So these three information are with light always. Okay, so F is frequency. If you remember, frequency is measured in hertz or number of oscillations per second. This is wavelength, length is measured in meter, and speed is in meter per second. Like you know that light in vacuum, it travels with 3 into 10⁸ meter per second. Now what happens, these all three variables are related like this: frequency equal to this by this, right? Now we are going to talk about that in refraction what parameters will change and so on. So these are three very important parameters with light. Okay, now let me pose some more questions, then we'll talk about it. If you guys can remember, how you can burn a piece of paper with a magnifying glass. So suppose you have a magnifying glass and there is a piece of paper. You can imagine like sunlight is hitting this and you can burn this. So what was happening, suppose there was no glass here, so what was happening, all the light was hitting, the entire light passing through this area was hitting this much boundary, right? This is paper boundary. Now with the use of this lens, what we have been achieved to do, or what we have been able to do, is that we are targeting all the light at a single spot. So just imagine this much water is going through the pipe, okay, and imagine all the water concentrated now at this point of the pipe, okay, in one way. So you guys can imagine that this entire energy is concentrated at this point, so we see as an image. So that is a not good analogy what I said about water and all. So what we are doing, if we are putting a lens, we are being able to converge all the light into one point, and you can see if the entire energy is concentrated at this point, the temperature will increase and it might burn and so on. Now there are also very important characteristic when we deal with refraction. Like if I ask you what is the difference between glass and diamond, In one way they are same only, both are glass to me, right? Means they are transparent and so on. But of course we know that diamonds are very costlier than glass and so on. It has to do with the fact that we'll talk in terms of refractive index, or it is called optical density. Now what we are going to explain is what is the meaning of optical density. So optical density, or it is also called refractive index. In your book it will be denoted by mu. Okay, and I'm going to use the word n. So let us take the simplest example, like suppose we all see glass. Suppose glass and air, two mediums are interacting, and suppose I had a laser light, okay, and this laser light, just to tell you one important thing, laser light is a monochromatic light. White light is not a monochromatic light. White is mixture of all colors, and that is discovered by the phenomena dispersion. Okay, so in all the experiment generally we, unless mentioned, we'll talk about laser kind of light only, monochromatic light. So what happens as this light comes and suppose hits here, and then it goes into glass, right? So at the point of contact we'll draw what is called a normal. So this is called normal, and the angle between normal and this laser ray is called angle of incidence, right? Now suppose there was no glass, then the light could have traveled in this straight line. Because of the presence of glass, and because glass is denser than air, the light bends towards the normal, and I am writing this angle to be r. This angle is called angle of deviation. So I is the angle of incidence, r is angle of refraction, and this is angle of deviation. Okay, so this is deviation angle. Now what happens if light is going from one medium to another? Let us say we are denoting air by medium 1, medium 2, then refractive index of this combination is defined as refractive index of second medium with respect to 1, and that is equal to speed of light in the first medium by speed of light in the second medium. This is the definition of refractive index. It is always defined with respect to something. So refractive index of medium 2, which is glass, with respect to medium 1 is speed of light in the air by the speed of light in the glass. Now in your book they might be using this symbol, so this symbol is also same. Now in general this will write refractive index of glass with respect to air, and that will be equal to speed of light in vacuum, we write it by c, and speed of light in glass we are writing by v. Now refractive index of glass with respect to air, you will find it out in the book, it is 1.5. One more example I will write. Refractive index of diamond with respect to air is around 2.4. So now this word actually makes more sense, optical density. Okay, now optical density is different from your mass density. There is something called density equal to mass by volume. That concept is completely different. Optical density of diamond is more than the glass, right? If you talk about kerosene and water, both have, of course kerosene will float over water, so kerosene have less density in terms of Archimedes principle I am talking about. But when you talk about optical density, it's how light is reflected back or how light gets deviated inside the medium. Okay, It has nothing to do with the density equal to mass by volume concept. It has to do with light, how it bends the thing. More the optical density or more is the refractive index, more we'll find that the speed of light decreases. Now going deep into this is, let us say we have this refractive index of glass with respect to air is 1.5. Now what we mean by that, if you use this formula, then 1.5 is equal to C by V. I am using this formula. Now V is equal to C by 1.5. So C is 3 into 10 power 8 by 1.5. Okay, now try to understand, if refractive index of glass with respect to air is 1.5, it means that speed of light in glass is 1.5 times less than that in the air. Okay, and if you can see that it turns out to be 2 into 10 power 8 meter per second. So let me rephrase it again. The speed of light in glass is 1.5 times less than that in the air. Okay, so more the refractive index, more light will slow down into it. So if you see diamond, whatever table is given, I guess diamond has a maximum refractive index or optical density. It means if you compare diamond and glass, in diamond actually it slows to a greater extent, and I guess because of that fact actually it is cut in a proper way so that light gets trapped and it travels for a very long time till it comes out. So you can see the comparison is that light will travel very slow in this case, in case of diamond. Now coming to the angle of deviation is this. Okay, now I want you guys to take this actually more than laws of refraction. There is one interesting thing. Suppose your friend is inside a swimming pool, let us say here. So this is your friend and he or she is drowning, and you are here on land. I guess you guys can imagine it. So this is flat and there is someone inside the water, right? So if you want to save your drowning friend, actually if you run the way the light has run, that will take the minimum time. So let me put it like this. Suppose someone is drowning in a swimming pool at that location and I have to run from the ground to save him. I will take the path which will take minimum time. So same way light takes the minimum time to reach from one point to another point. Now we'll talk about this thing again. So refractive index of 2 with respect to 1 is defined like this. Same way refractive index of 1 with respect to 2 will be V2 by V1. Okay, just follow the same analogy. This one N21. So N12 means light is going from 2 to 1. 2 to 1 it's going. So if light goes from 2 to 1, then we'll define refractive index of 1 with respect to 2, and which will be speed of light in the first medium, then the speed of light in the second medium. In this case also, okay, refractive index of 2 with respect to 1 is first medium and second medium. So you have to see how light goes from one medium to another medium, then you can write down these formulas. Now if light goes from 2 to 1, we can define like this. If light goes from 1 to 2, we can define refractive index like this. Now if you see that, then you can also see that N12 into N21, which will be V2 by V1 into V1 by V2. So that will be equal to 1. So this is one important relation, right? Now in your book, textbook, all the numericals on this chapter are based on this thing. Okay, I will just add one more part into it. Now, in refraction, frequency remain constant, but lambda, which is wavelength, and speed changes. Now, this is one amazing fact about refraction, that if you have medium 1 and 2 and it's going from, let us say, medium 1 to 2, then as it goes from this to this, frequency remains same. Now actually, why it remain constant? Frequency depends on the source. So suppose our source is a laser light. So if it is going from 1 to 2, the source is not changing, right? The source remains laser or its circuit which is producing that light. So frequency will not change. Why frequency will not change? Because the source is not changing. Frequency depends on the source. Okay. Now, so frequency remain constant, and this will change. Now you can see that frequency is equal to V by lambda. So suppose frequency is 20, let us say. So how this and this will change so that the frequency remain constant? So if frequency is 20, you can imagine this can be 200 and this can be 10, let us say, and something different, 2000 by 100. So this number can change. If you divide it, the frequency will remain constant. We'll see how it changes. Now, frequency in medium 1 is equal to frequency in medium 2, and using this relation, frequency equal to V by lambda, we will get V1 by lambda 1 is equal to V2 by lambda 2, and so lambda 1 by lambda 2 will be V1 by V2. Now if you can recall, lambda 1 by lambda 2, this is nothing but refractive index of the second medium with respect to 1. So this one will give us lambda 2 is equal to lambda 1 by n2 1. Now to understand this, let us say this is air and glass. So this tells you that wavelength in glass is equal to wavelength in air by refractive index of glass with respect to air. So refractive index of glass, wavelength inside the glass will be equal to wavelength inside the air divided by this factor. Okay, so this is all about optical density, and as I told you, in the next video I am going to start laws of refraction. But all the numericals of your textbook of chapter 4 first part will be covered by this much. Okay, so that is your assignment for this video. Thank you.